welcome back. We only have 2 talks this afternoon. For everyone in person, I hope you really enjoyed your GDT and other telescope tour on site. Our talks today are both on observing and calibration. So Dave will kick it off with continuum observing and calibration. I will follow up with spectral line observing and calibration. You'll see there's a lot of overlap between these 2 areas. So we've worked out some things that could belong in either of them, and we have moved them into either the continuum or the spectral line talk. But after that, then we have your 20-meter observing starting at 3:30. So take it away, Dave.
Okay, thank you, Will. Yeah, as Will said, we've divided up some of the topics on this talk. And a lot of this has been collected over the years, and it's been focused on the GBT. So it's, but we try to make it fairly general here. So topics, we covered, you already had continuum emission mechanisms. Larry on Monday, if you remember, you have synchrotron, free, accelerated particles, gives off radio emission. Ryan talked about pulsars yesterday. I wasn't there for that, but I'm sure that went well. So I'm not covering that. Mapping, I'm covering on Thursday. A lot of times we include it with the continuum. And then we have the spectral line. Will's going to do spectral line, and I'm going to do continuum observation. So I'm going to go give a little bit of background, just a little science show and tell with continuum. Talk about confusion, 1 over F noise, different continuum observing techniques, get into some calibration. And then as an aside, this could be spectral line as well. I'm going to go into the temperature scales and efficiencies. A lot of times in radio astronomy, you just talk about aperture efficiency. I know my group, we're measuring, like, in principle, the aperture efficiency of the 20-meter, but we have a lot of efficiencies, especially in millimeter astronomy. How many people have used the 30-meter or done millimeter astronomy? Very many? Nobody? Have you've heard main beam efficiencies, forward, there's like all this sort of jargon. It's its own jargon in the field. So I will expose you a little bit to the terminology we use primarily in higher frequency millimeter astronomy, because, well, it's an important area. There's a lot of times in radio astronomy at the low frequency, and we don't worry about a lot of these terms, where as we move up into higher frequency, we do. So the radio sky, if your eyeballs were radio, you know, could pick up radio waves, and you looked at the night sky like this image. So this is a radio image of the sky taken with the old 300-foot telescope. Here, this is obviously an old picture because it no longer exists. It fell down in 1988. But this is what the sky would look like if you looked up. And most all those little point sources, instead of being stars, they're AGN, typically pretty far away, a redshift of, you know, whatever, point few to 0.1. So they're all distant. Most sources you see in the radio wavelengths are extragalactic, very distant AGN. And Larry showed you this, and this is a nice overview if you just to understand radio emission from galaxies. So you have the synchrotron emission. So at low frequency, when you look at the sky, radio waves, you're seeing all synchrotron emission, even in our galaxy. And our galaxy is like supernova remnants and such. And then the external galaxies are, you have the AGN. So they emit the synchrotron emission that dominates at low frequency. At high frequency, those are coming from the infrared or the millimeter, submillimeter regime. It's all thermal. It's a black body thermal. But the tail of the black body dies away at a lower frequency. So that's only important up at the higher frequencies within the ISM. You know, temperatures, whatever, hundreds to, you know, a lot of cold temperature down to 10 Kelvin. In the middle, you have the free, which we call thermal. It's also related to thermal processes like H2 regions and such. That's electrons that are just get accelerated as they go around protons. So this is a general spectrum. AGNs, I assume these, you've seen pictures of these, are quite spectacular. But things to keep in mind, the cores of AGNs, they can be highly variable, and they can be bright at high frequency. So like for very high frequency calibrations, like at 3 millimeters, we use the brightest radio sources, and they're super bright down in the cores, but they're very variable. So they're not very stable. So they're not very good as calibrators. So you have to track them. The lobes themselves, they're much more stable. They don't change as much, and they dominate at low frequencies. So when you observe at, you can observe the same source at lower radio frequencies, like at L band, you'll see these huge radio lobes, but then if you went up at higher frequencies, you can be core dominated. The crab nebula, this is synchrotron emission as well. The supernova remnant, it's a beautiful image of the crab. So this is basically synchrotron emission associated with the supernova remnant. Now flipping completely a little bit, that was all synchrotron emission. This is actually 90 gigahertz continuum emission. We have an instrument called Mustang 2, the second version. A bunch of feed horns, those really cold. It's taken thermal images of the sky. So this is within the Orion Nebula, and this is a cluster. So it's used a lot for studying the cluster dynamics, a high redshift. Did Emily give her talk already? Did Emily give a talk? So she did, the SC effect. So basically you have the cosmic microwave background scattering, it gets hot X-ray gas. You actually see it as a negative signal in the radio. And beautiful picture of, this is from Arecibo at L band, and just galactic supernova remnants, H2 legions. And the background again is all those point sources are extragalactic backgrounds. The southern sky, hold this up. I did last year, I did. I just thought that was sort of cool to show. But here's the galaxy. Normally we're used to looking, a lot of our objects are up in the northern sky, but this is what they see down under, so to speak, in Australia, where the Parkes telescope is. And you can see the galactic plane. This is galactic coordinates, and then some of the common objects. Like, so we were looking at Virgo A, 3C274, M87. Now, if you go to the microwave background, you remove the galaxy, and you look at the background. You have to remove all foreground studies, study the background. This is from a Planck experiment, and this provides a nice. This drains on cosmology. And this is an image effectively of the sky. If you look from the NRAO BLA all sky survey, it was at 45 arc-second resolution, L band, basically covered the whole, basically the whole sky visible for the BLA. And so if you look at it at this resolution, all these things here are extragalactic point sources. The galaxy you can see is here, but these are all AGN. I'm going to zoom in. So this is just looking at sources brighter than 100 millijanskis, and so we're going to zoom in there on the next slide. So this is then it's still completely packed with objects. This is down to 2.5 millijansky. So lots of sources, very isotropic, and basically, I should have fallen into, well, okay. I should have put this slide first. I should have moved this around. But anyway, we're going to jump into the confusion noise, because since there's so many sources in the sky, single dishes are obviously all dominated by having a floor in which you can observe down based on the confusion noise. So normal observation, you have the standard noise of your instrument. You have the confusion noise for single dishes, very important. The 1/F noise, which Larry had mentioned as well on Monday. You have underlying total power baselines, and we're also impacted a lot by RFI. If you're trying to make a total power measurement, the RFI comes in. If it's not in a narrow band, like the pulsar people, you can break it out and ignore it. But if you're just looking at the total power and RFI comes in, you can get pretty corrupted. So the confusion noise is just a graphical. I mean, this is pretty easy concept to understand. We have tons of tiny little radio sources that over the entire sky. There, so there is no blank sky, and this is effectively what the GBTB would look at. And this is the NRAO VLA survey. So these sources, the resolution here, the underlying resolution is 45 arc-seconds with the data. And then if you compare the 300-foot data, which would be similar to the resolution of the GBT, 100 meter, 300 foot, a little bit better at 9 arc minutes. So 300 foot at a 12 arc minute beam, that's what these contours are. This is data for the 300 foot, but the underlying deeper VLA image down to 45 arc second, you see underneath it, so you see all these faint sources. So you see almost all sources that you would pick with the 300 foot are comprised of multiple sources. from the DLA observation. And you can sort of quantify this, and you can derive the confusion noise. This power law here is just the spectral index of the radio emission. That's what synchrotron power law is. So if you go to higher frequency, the strength drops. And if you look at it this way, like for the GBT, so the bigger your dish, the lower your confusion limit, because the beam is smaller. And so this is confusion noise for the GBT. It's 50 millijanskis, and the power law is minus 2.7. So the minus 2 comes from basically as you go at higher frequency, the beam gets smaller by it goes by the beam goes down, the beam size gets smaller by a factor, a power index of minus 2, and another minus 0.7 comes from the spectral index of the sources themselves. As you get to higher frequencies, the sources themselves get thinner. That's why you can, if you go to higher frequency, the confusion noise drops like a rock. Okay, so that's confusion. The 1 over F noise, that's the additive effect we get for single dishes. You do not get this for interferometers, because the interferometers, they do the signals, the total power signals don't correlate between receivers. You're looking at cross correlation, where with a single dish is like an auto correlation. So you're basically stuck with it. Like when the single dish is looking at that, whatever you see is what you see, and it's a total power. So you get the 1 over F. In the old days, the instruments, the amplifiers themselves weren't very good. They're much better now, but you still have a 1 over F noise, and you get atmospheric effects at higher frequency. Also, sort of mimics the same thing as 1 over F noise. It's just variations as a function of time. If instead of looking at, just think to look at blank sky, you just look at the same spot. Ideally, you would see the same signal, but you don't. You see it drifting around. I'll show you in a few more plots. So this dominates basically for single dish, unless you build a specific type of back end. And we do have that. That Caltech Continuum back end for the Ka band receiver has a very fast switch. I'm not sure if anybody's talked about, we probably haven't talked about Dickey switching, didn't?
No.
Nope. Okay, we didn't talk about that. Yeah, that's in general radio astronomy. People, so if you had you could have 2 horns, you can switch really fast between them, and that allows you to basically mitigate this effect. So if you take a power spectrum, and this is what it looks like. So for an example receiver, so I did this a few years ago with the 340 megahertz receiver, just to test and see its performance. And here, this is what we call the 1 over F noise. So the power spectrum is a function of frequency, where time goes this way. So maybe that's easier to understand depending on how you like to look at frequency domains or the FFT domain. So this is 1 second. So everything longer than a second is over here. So then it's the knee of this spectrum, this power spectrum increases here. So anything longer than a second, you get extra noise basically. You can't beat this down by having larger bandwidths or anything else. So the 1 over F noise dominates for longer integration times, and it can be 1,000 times higher. So the noise can be 1,000 times higher. So a lot of times people say, "Oh, I'll do a an hour observation on something, and I'll be able to go down." No, in an hour observation, your noise levels are so much higher than you would expect if you don't include this. So if you back this out, let's say if you want to try to mitigate this, you can sample the data really fast. For the GBT itself, for this particular case, to remove this 1 over F noise down here, we'd have to slew at 6 degrees a second with the GBT, which we can't do. The 20 meter can slew at 2 degrees per second, which is much faster than the GBT. So it's impossible with this current receiver to basically beat this 1 over F noise down. So based on these tests, this other group, they wanted to make a measurement at 340. So they built a new receiver to mitigate this, a new receiver structure. And that actually receiver is under construction and should go on the telescope this fall. So how do you beat it? You do what we call, what I mentioned before, a Dickey switch. So you can imagine you have 2 feeds. and the signals are coming in. You can have a switch going back and forth quickly between the two different beams, basically. And then that allows you to beat basically, if you switch faster than the noise variations, then you basically subtract that off. And this technique, basically, if you do the math a little bit, you do your normal on minus off, your on has the source plus the other stuff, and the off just doesn't have the source, and basically you subtract that, you get the gain times your source, you just get the source plus this thing, the delta, whatever the difference in the gain was in between the two times plus everything else. So if you switch fast enough, that delta G is basically small, so this term goes away, allow to basically measure your source. There is a downside of doing this in a sense of your noise. You basically only spend half your time on source because you're switching back and forth. So you lose a factor of 2 there. And if you do an extra subtraction between the two beams, you get a √2 in terms of increase of noise. You take 2 equal distributions and you subtract the 2, the noise goes up by √2. But this is vastly better than I'm dealing with the 1/f noise. So you get 2 times higher noise than you would expect if in an idealized case, if you didn't have to do this. Just in comparison between the 1/f with, this is a digital continuum receiver or default backend versus what we get with the CCD with this fast sticky switching in terms of the power spectrum of the noise. So the dashed line's the idealized theoretical case. So the red shows what you get with the CCD with this fast 4 kilohertz switching. And then here's what we have with the regular backend that we use with the GBT. So all of our, most of our receivers just have access to this. This is their performance. We just have the KA band with the CCB as that special receiver architecture that allows you to beat the 1/f noise. Effective bandwidth for our different receivers, and what we mean is effective bandwidth. It's basically the bandwidth you effectively get that would match the radiometer equation and noise. So by increasing your bandwidth, typically what you do to increase your sensitivity, like with spectral line, you can smooth your data over a wider bandwidth, for example. Here, this is just the effective bandwidth. So like for the Continuum, we have backends that can have a gigahertz, but you can't effectively get a gigahertz. So if you're trying to estimate your sensitivity, you're basically like 2 megahertz is all you can use. So you could put 2 megahertz into the radiometer equation, and that would give you sort of the sensitivity you would get, expect to get from your receiver. There's a memo. You do NRAO GBT memos that are linked to the NRAO library. You can get all of our memos, but this one goes into the details. So if you ever do GBT observations, continuum observations, it's useful to check that memo out. So with the DCR, with the KA band, limited to 40 gigahertz of effective bandwidth. When you use the CCD backend, you effectively can use the full 12 gigahertz of the band. So you have the power of the full 12 gigahertz of the receiver versus being able to only use a little bit of the receiver for the continuum sensitivity. And this is completely different than interferometers. The interferometers, you keep winning by doing more bandwidth. They don't run into this 1/f noise. So confusion about 1/f noise. This gets people that put in proposals, as well as our staff and astronomers in general, because most astronomers these days actually have more experience with interferometers than they do with single dishes, I think is fair to say now. So we cannot mitigate the 1/f noise with increased bandwidth. I've been saying that. Some people are confused. You think they can say, oh, we'll use Vegas with small number of spectral channels. We'll have like these small spectral channels. It has nothing to do with spectral channels. Can't mitigate it with that. You cannot really mitigate it with multiple spectral windows because the noise is going up and down together. It doesn't matter how many windows and how much bandwidth you throw at it. And you can't mitigate it by flickering the noise diodes faster. That doesn't really matter. It's at a certain level. If you're flickering the noise diodes really slow, you can make it worse, but we're already flickering the noise diodes as fast as it would that we can to mitigate it. Flickering them faster isn't important. That's not the time that's important. Some people think that's the time that's important. The time that's important in 1 over F noise is the time it takes to do your on minus off observations. So if you're mapping a really big object on the sky, it might take a long time to map across that. So then that would be a large time scale. So then you're going to be well up on the, have a higher 1 over F noise. Even for point sources, it'd be the time it takes to slew across the point source. So if you want to mitigate 1 over F noise with continuum observations, the trick is scan as fast as possible and take as many observations as possible. So if you scan over your point source 100 times, the noise on each individual scan is going to be crummy and noisy because the 1 over F noise, but you can beat that noise down by the number of observations, by root in an number of observations. So that's the trick for point source and 1 over F noise. Okay, observing strategies. The antenna temperature. We use the term antenna temperature. It's not a very pretty slide, sort of, but anyway, the antenna temperature is the source plus all this other stuff, the receiver, the background, the atmosphere, the spillover. So everything in curly brackets, I'll just put other contributions. So the whole trick in how we do radio astronomy typically is relative measurements. And this is true for spectral line as well as continuum. You measure on observation and you have some kind of reference. So your signal minus your rep. And the idea there is you subtract the two and then you're able to measure your source. So the whole goal in radio astronomy observing techniques is different ways for measuring on minus off. There's two main ways, frequency switch and position switching. For continuum observations, you don't use frequency switching because you're subtracting continuum minus continuum, so that's not helpful. So, but we do use position switching. Frequency switching is used in spectral line for narrow spectral lines. You can do position switching with mapping. You can have a reference off. We have these modes here. We don't necessarily get into it. These are actually boldface are the commands that we give for the GBT. We can nod the telescope between two different beams, and we have a subreflector that moves sort of slowly every 5 seconds. We move it roughly to switch between the two beams. Since our telescope is so big, it takes a lot of time to move, 17 million pounds from position to position. A lot of radio telescopes, the higher frequencies, they have a much better subreflector, a much faster subreflector. They're smaller. Our subreflector is still pretty big. It's 11 meters or 8 meters? Eight. So it's still a big thing, moving back and forth. And so it's not designed for idealized continuum observations. At the 140-foot way back in the day, it would have a subreflector and it could go back and forth like at 5 hertz or something like that. So if it's doing continuum observations, it would be going really rapidly back and forth, and then we'd move it slower for spectral line observations. And then I mentioned the beam switching. So, okay. What was it? Continuum observations. So these are just some points here. Obviously, you need to be bright sources to detect it above the 1 over F noise level and confusion. You benefit from fast scanning with to mitigate the 1 over F noise. These are just general points, so I'll go into more details. Like maps can be done in multiple directions. You ever hear basket weaving? You map an RA and then you map a depth. And that way you can remove some of the systematics. And then for the continuum observation key thing, especially for small structures, if you're not mapping a really large structure, small structures, you can filter the data in the time domain. I mean, this is very powerful. You can take a data stream and you just do a median filter across it, and you remove the waffling stuff, and that removes that 1 over F noise or the total power baseline. You basically subtract the running median as a function of time. And that's very powerful and needed for continuum observations. As an example, here's the atmosphere. This is at 3 millimeters, but it shows their atmospheric variation. So the sources here, these things here in ovals. Everything else is just variation of the sky. So you see the sky is going all over the place here, but you can filter this data and recover all those point sources in the data. Continuum. Another example, this is more in bolometer. This actually came from the Herschel's Frayer instrument in the infrared. A lot of times bolometer instruments share a lot of readout electronics and such, so they have a common noise. So all the bolometers see the same structure. So this shows two different pixels within the Frayer, and they have a similar noise. So basically, they share that same noise. You flatten out that instrumental effect as a function of time, and that flattens it out, and that will clean up, flatten your data and allow you to make a much better map. So it removes that noise. The basket weaving technique, there's a couple of references here. So if you just have one direction and you going through the default reduction, you see residuals along the scan direction. If you map in both directions, combine that together, and you can basically mitigate that. So example techniques. Will's going to talk about noise dial, hot and cold loads, and absolute calibration. I'll just give you a little background, and then I'm going to jump into some aspects on not just with the continuum, so the temperature scales that we mentioned. So if you're measuring the power, I think by this time maybe you've seen some of this. People write this in different ways. I'll leave this on the slide. I won't necessarily go to all the math, but the power that you receive is some scaling gain. This is its gain RF and the gain due to the IF system. And then your receiver temperature, and then what your telescope's measuring is the source convolved with the antenna pattern. So this is TA. So this is basically the antenna power pattern on the sky as a function of like two angles, like this angle and that angle. So it's an integral over the brightness temperature of the source structure on the side. So you can imagine have a source structure on the sky, variation as a function of angle. So that's what TA is. We have the non-source sky components, the cosmic microwave background, the atmosphere itself. So the microwave background signal is basically being attenuated by the Earth's atmosphere. The Earth's atmosphere, you see it both in emission as adding a contribution because you're looking at as well as the absorption through the atmosphere. And then you have a component due to the ground. So 1 minus this factor here is what you see in the sky, eta L. It's like an efficiency. It's like what fraction do you see on the 2 pi in the sky. So 1 minus eta L is what fraction of the antenna power sees the sky. I mean the ground, excuse me, ground spillover. We have all these contributions here, and the system temperature that we measure is everything in these square brackets. It's everything. So when you do on minus off, you have a source plus all this stuff in the on, and then when you do the off, you just have all this stuff, and then in principle you subtract all that stuff, and you're left just with the source. So they're slightly different in the way we calibrate in general, continuum versus spectral line data. Like the spectral line data, and we'll get into this, we actually do a signal minus a ref, and we divide by the ref and that reference in terms of the passband. That helps remove some of the baseline structures. For the continuum, it's a more of a direct calibration. We do our signal minus a ref, just scaled by the ratio of the noise dial and the counts that you see when the noise dial is on and off. So if you have a noise dial, you turn it on, it has some temperature, let's say, and it's the same thing, on minus off. So when it's off, you have the gain times the receiver temperature plus all the other stuff. When it's on, you have this additional thing. When you subtract the two, the only thing that's left is the T noise dial. And then from that, you can derive these gaining factors. And those are just scalar factors. So basically, TA is just these gain factors times your signal minus the ref. This ratio here just gives, it's just a scaling between counts and Kelvin for your instrument. Maybe that's the easier way to say it. The flux density versus antenna temperature. We've done this for our group since we have to measure the aperture efficiency. So, this might have been covered a little bit already. But the specific power that we receive, the antenna receives, if you can basically equate that from the source density, source on the sky. So if you see a source on the sky and flux density watts per meter squared per hertz, how much power you see there, you can multiply by the meter squared effective area of the dish. The 1/2 power is due to the fact that this equation, when we're looking at it this way, is just looking at one polarization. So we're seeing half the light. And then you equate it to the antenna temperature measure, this K, that's a Boltzmann equation. So the specific power is just K TA prime, and TA prime is corrected for atmosphere. We'll get into that in a little bit. But if you just run this through, you get a general equation. This applies for all radio telescopes. For the GBT, it's this, and then you can just get the aperture efficiency. So the 20 meter will be different because we have a different diameter dish. So that's point source calibration. You basically, you can measure an aperture efficiency. You observe this, you know what this is by somebody else has wrote a paper and it gave you the flux densities, and you can estimate the aperture efficiency of your telescope. If you have assume a Gaussian beam, you can go through, one could go through the math and compute the effective, what we call beam efficiency. I'll give you a mathematical form for it in a few more slides. Anyway, if you do the math, you get that, and that is only applicable for a Gaussian beam, which is pretty close. And we tested this out with the GBT even up at the highest frequencies. This works at lower frequencies, but what we've demonstrated even up at the highest frequencies of the GBT all the way up to 115 gigahertz, we see basically the theoretical expectations of performance of the aperture and beam efficiency. So by measuring a whole bunch of quasars, this is back a few years ago, we measure the aperture efficiency as a function of frequency, and then also measure the beam efficiency based on the size of the beam. And what we found was this ratio here between eta main beam to eta L, and that correspond to the beam full width half max equal to basically 1.2 times lambda D, which is basically in line with theoretical expectations. So here, now telescope efficiencies, this might bore some people, I apologize, but I think it's useful to go over. These definitions are from Kuttner and Ehrlich, 1981. If you ever do millimeter astronomy, I would highly recommend looking at this paper. It's a nice paper to go through, and it gives a lot of the background. But we use a lot of different terminology in terms of efficiencies. We have the fraction of power in the forward 2 pi direction. So the antenna has power. There's a power everywhere. The fraction of power the antenna sees in the sky is basically this eta RSS. We typically refer to that as just the eta L because the ohmic efficiency of the metal is 1 roughly. If you have a telescope that wasn't very, let's say make it out of some wood metal alloy, so it was like a lower fraction, then that would be lower. But all radio telescopes, this is normally 1. So a lot of times we call this forward efficiency eta L. We refer to it as just eta L's. So that's in the forward direction. We also have, well, we call it, this is the confusing part in the terminology. So power in the forward direction, but they call it the rear spillover and scattering efficiency, just to confuse people. So that's where the initials come from. But so the inverse of that is basically the fractional power in the forward direction and 2 pi in the forward direction over all 4 pi stereo. So the full sky for people, is 4 pi stereo is everything, and 2 pi is above the horizon. So the forward spillover scattering fraction efficiency is a fraction of power in the diffraction pattern of the beam. It actually includes the air beam as well, compared to the total power in the forward direction. So so you have a beam, you have an air pattern. It's the amount of power in there compared to 2 pi stair radius. And the other term which you'll run into more often. So these are more, we use them sort of theoretically, but in papers, people talk about main beam efficiency. I'm assuming people heard of main beam efficiency. So that maybe is easier to conceptualize. It's the power and your main beam, the fractional power and your main beam over all 4 pi stereo. So integrated over your main beam over all 4 pi stereo radius. So all those efficiencies, they come with different temperature scales. Different telescopes use different temperature scales. The GBT at low frequencies just uses antenna temperature. But if you work at higher frequency, you want to correct for atmosphere. So TA prime is the antenna temperature corrected for atmosphere. Most millimeter telescopes today will use TA star, and we use that at higher frequency. So that's the major antenna temperature in the forward 2 pi direction. That's good for extended sources, so it's power forward direction. We use this term with the 12 meter. So a lot of times Europeans will refer to a US temperature scale because it was just done with the 12 meter. Nobody else adopted it. The JCMT adopted this, the TA star. But anyway, and 12 meter is not being used now, but it's a combination of both the eta L and the eta FSS. So anyway, arguably it's a closer correction to the actual temperature on the sky. So the idea here is you measure different temperature scales, but you really want to know what the real temperature of the source is. And then like how you go from measurements to physical reality, it goes into these different telescope efficiencies. And then eta main beam, again, this is maybe concentrate here. This would be the easy one to understand. It's a fraction of power in the main beam, so that what you see in your main beam is reflected to the measured antenna temperature. But anyway, TA prime, that one corrected for atmosphere is just equal to the rest of them. So each one of these, so if you're talking main beam efficiencies, if you're talking that, then they need to know eta main beam. If you're doing TA star, then the term that you're interested in, you need to know is eta L. If you're talking TR star, then you need to know eta L and eta FSS. And like I said, that Kuttner and Ehrlich paper really lays it out sort of consistently. Okay, so let's say you want to measure T main beam versus team source. How do you do that? A lot of these integrals are difficult to compute. You can compute them theoretically for if you had assumed a Gaussian beam, but if your beam's not Gaussian, your source isn't Gaussian, the math can get quite complicated quickly. So this is just a schematic on showing how we approach this. So the eta main beam is basically integrated over the antenna power spectrum over your source. And we can compute this in specialized cases, which that's what most of the time we do in astronomer. Astronomers tend to make approximations. So if your source temperature is uniform and it's really small, T main beam, much smaller than the main beam, then the antenna, the relative antenna power is 1 over the source. Going back here, power spectrum is normalized to 1. So if the source is tiny with respect to the beam, you're up at 1. So that makes an integral easy to do. Even I can do that. You can pull, that's 1, so you can pull that out. So then it's basically the T main beam is just your source power integrated over the main beam. So it's the integrated over the source, excuse me. So it's just a ratio. And this goes to explain, like when you ever hear the term beam dilution. So if you have a very small source, the fractional, the temperature you measure isn't what the actual source is because it's being beam diluted. Your source is only covering a small fraction of the beam. So the effective temperature that you measure in the main beam is the actual source temperature scaled by the fractional areas of the source versus the beam. So that's where the beam filling factor comes in. So if you're comparing data, like temperatures from different, like let's say you use a 30 meter and a 100 meter, with different beams, they might see different temperatures, but if the source is small, you can get factor that in. And a lot of times, the GBT, the brightness temperatures will be much brighter for little clumps because we have less beam dilution because our beam is smaller. So people that come from the 30 meters, wow, this line is really, really bright. And it's just the fact that our beam is small, they have less beam dilution. That's why it looks really bright. There's another, this is a more generalized case where if you say the source is Gaussian and then the beam is Gaussian, you can go back and do these math. So Gaussian and Gaussian. It's easy, you can do the math easily, basically analytically, and what you get, what comes out is this. And then if you look at the two extreme cases, let's say the source is much smaller than the beam, so that goes away. You recover that and go in the opposite case, which we use a lot. The source is much bigger than the beam. Then if the source is much bigger than the beam, then this just goes to 1. So when the source is much bigger than the beam, what you measure is what the source physical temperature is. Modulo, you have to correct for the Earth's, the absorption to the Earth's atmosphere. So those are the two extreme cases, not extreme cases, limiting cases that one can compute analytically. You can also compute this analytically for when we do this for planets. A planet's a disk. We can involve a disk with a Gaussian beam. If you assume the planet's a disk and then the beam's a Gaussian, you get an expression like this for the main beam efficiency. So that's how we go between measurements of objects of the sky and connect that to the temperatures that we observe. In terms of the calibration, Will is going to go in this and show the different loads, but at higher frequencies, what we have, we can what I call direct calibration versus TA star calibration. I think this is useful just to quickly summarize. When you have the direct calibration, we use that for what we call the W band or the 4mm receiver. We have an ambient load, a warm load just at room temperature, and a cold load. And you can basically derive the gain because you have the two temperature scales, you have the two different counts, you get the scaling between Kelvin and counts. And then you could calibrate this, but then to get the calibration, you still need the opacity of the sky, which we have models for. And this expression here is just an empirical lab measurement relationship for that receiver. The beauty of TA star, and it is quite amazing, if one goes through the algebra and looks at this, is you can take a temperature sensor, you put it on an ambient load, you can calibrate the daggone temperature scale without even knowing what the heck's going on with the atmosphere, and you don't even have to know what your spillover is. It's a quite remarkable statement. They figured this out in the, I guess, the late 70s. And that's why it's glossed under, but that's why that Kuttner and Olick paper is worth reading if you ever do millimeter astronomy. And so this TA star, how it works is if you have the TA star, you have some temperature scale, TCal, which we don't know, and you count on minus off, basically. And then you versus the ambient load. So that's like source, signal ref, that's the warm load, the counts on the warm load, and then that's the counts on blank sky. So basically, instead of doing between two known loads, like a cold load and a warm load, you do a warm load and blank sky. You take that difference. And even though you might not know much about the blank sky, like what the tau opacity is, when you go through the algebra, it basically, a lot of the terms all cancel away, and it's quite an amazing that it can basically reduces down to this TCal that you need to do the calibration, just basically just your ambient T temperature measured by the sensor, the ambient temperature. For us, for the GBT, when I went through and did this, it was a lot of, I ran through it. It's the batteries, I overheated them there. I got usually at most other facilities, it's usually 10, 20% off. But when we ran it through the GBT, it was 1.0, 0.997 plus or minus 0.02. So it's basically quite impressive that works well. And the reason it works well is the fact that for us, part of the reason, this eta L is near 1. And then the ambient and the spillover. Usually what people assume is the ambient and the spillover, and that cancels out a lot of the terms. But we have an added benefit since we have no spillover that near 1, there's a great approximations, and then you can basically the terms come down. That's okay. It's okay. So we don't necessarily need to go through the algebra. The algebra is interesting going through it. You can learn a lot. But this is why you basically, with a simple temperature sensor, you can basically calibrate the telescope independent of what the atmosphere is doing. The different terms that they cancel out. What we do, since we know what the atmosphere is, we have models and predictions for this and this. So we actually do compute it with Argus or other receivers that we can compute these terms. Basically, they come in second order. But you don't really need to hardly because it doesn't really matter. So the GBT at the highest frequency, this is like 80, well, not highest frequency, this is a nominal frequency we use as a metric to calibrate its parameters, a whole bunch of parameters here. For those that work at higher frequency, this took a long time to get to where we are, where we're able to achieve this performance. 20 years of people working on improving the surface of the telescope achieved this performance at 3 millimeters. The telescope was built with hope to do this, but it did take us a while to get there. And sort of bottom line, even with the GBT, what I always thought, so there's power in the forward direction. So almost see everything sees a forward direction, but if you multiply it by this forward spillover fraction, this is the fractional power in the forward direction inside the beam. So almost all the power is within like 1 degree of where you look at in the sky. We don't have scattering off the feed arms and stuff. And that what holds up even at the highest frequencies. And that's all I had, and I didn't run over too much, but I didn't talk too much about, nobody cares about the efficiencies, but maybe we'll just keep it in an appendix in the future. So, but any questions on anything on continuum observing or calibration?
First of all, thank you, Dave.
And I promise you will have less math.
I'm a simple man. Yeah. Any questions?
I'm very
for Dave?
simple too. It's easier to understand if you see the map though. I don't know. I guess different people look at things differently. Yeah. Can you explain the dual beam switching? Dual beam switching?
Yeah.
Yeah. Will go over that, but so some of our receivers have two beams. So you have 2 beams on looking at it. So you can basically put your source in one beam and then put the source in the other beam.
Physically,
The telescope can move and put the source. So you have this into 2 beams. And the idea of using dual beams is if you do position switching on off, you lose half your time.
Yeah.
So if you build another beam, you save half your time on your telescope if you're just doing position switching. So we call it nodding. We can nod the telescope, but for the GBT terminology, nodding between the 2 beams. We put, the source in one beam versus the other beam. We call that nod, and we do that by moving the telescope. We have a sub-reflector we call sub-beam nod. Same thing, the telescope doesn't move, but the sub-reflector moves to change the optical paths. Yeah, and a lot of smaller radio telescopes have that. You can move that sub-reflector really fast, and that helps remove like instrumental effects. Okay. Our next speaker is the esteemed Will Armstrong. Oh, you have a question? Oh, I'm sorry. I forgot the online people. I apologize.
So with calibrating sources larger than the beam size at higher frequencies, what other considerations do we need to keep in mind?
The air patterns. So I glossed over the one because I figured I was rambling on too much, but with the, you need to know the coupling of your air beam with the large source. So, and that can be important. So an approximation is you say when it's larger than what you're going to measure, your main beam will basically be similar to your source structure because the source is much bigger than the beam. But that's glossing over a lot of complications with, you can have a complicated beam pattern, and there's a term, oops, I glossed over what we call a coupling. For an extended source is larger than the main beam, you need to know the detailed beam pattern, and we have this extra coupling efficiency for source. So if you're the GBT, we're fortunate with the GBT because we don't have our side lobes are way low because we have an off-axis feed. For the more traditional radio, telescopes, you really need to understand your beam and your air patterns to basically figure out the fractional power. So even though the levels are down really low, like in the side lobes, the area that the side lobes can cover on the sky are really big. So you can still have a lot of power in these side lobes, even though they're down on a low level. So yeah, that's a good question in a sense. I glossed over that, but yeah, you really have to worry about the coupling of the source with the air pattern, the beam pattern, the side lobes.
And for the GBT, there are routines already written that can do that for you. That can basically for L-band observations for H1.
Somebody's written a routine?
Yeah.
Okay.
So I think all Jay has to do is run a routine on it.
He has a spray radiation routine. Yeah. They had one for 140 foot. Jay had a grad student that was his entire thesis was quantifying this. Basically, the side lobe is 140 foot, so people could estimate these effects. Are there any additional questions online? Cool. Okay. Well, thank you for
anything else in person. Well, then thanks again, Dave.
We got one more last minute.
One more.
okay.
Sorry.
No.
When mapping an extended structure, what is the off position and how do you prevent from accidentally picking up another source emission point?
So there you have to know your sky. So there's different ways we do the off. In fact, I guess on Thursday I'll talk about mapping strategies. So you can map. You can go way off. So if you do a map, sometimes people will use the edge of the map if we're scanning across and use that as an off. But let's say if you're not on, sometimes if your source is really big, people you can actually go out of the galactic plane. So if you're mapping along the galactic plane, let's say you're trying to do a map over here and you want it off, you literally go out of the plane, get it off, and then come back. Which works at lower frequencies where the sky isn't changing that much, but at higher frequencies, it's challenging. You were signaling, Will?
I was moving.
Oh, I'm sorry. I just saw your motion like that.
There's tracking in there.
Okay. Yeah, we don't need to track anything. Okay. Thank you, everybody.
Thank you,
Will,
Dave.
Will's off the bat next.